Welcome to Center Math series on topology. Today we're going to talk a little bit about connectedness, what it means for a space to be connected. So we can define a space X to be disconnected if it is a union of two disjoint open sets contained in X. So this is essentially X equals U and V are some open sets, intersection of U and V is null. U and X is not null, there's at least some points of X and U, and there are some points of X and V. And if X is not disconnected, then it is connected. For example, if we think of these two sphere-like, circle-like shapes in R2, this as a subspace of R2 is disconnected. We can take the open sets to be all of one disk and then all of the other disk. These two are open subsets of this subspace. They have not null intersection with the subspace. They have a null intersection with each other, and their union is the whole subspace. So this is disconnected. But if we take one of these as a subset of R2, then it would be connected. Could not find two disjoint open sets whose union is the whole circle-like shape. So we can show if we have a continuous surjective map, F going from space X to space Y, and X is connected, then Y must be connected. So we can prove the contrapositive is Y is disconnected, then X must be disconnected in this case. So assume Y is disconnected, so we have some open sets U and V, union of U and V gives me Y, intersection of U and V is null, and U contains some Y, V contains some Y. So taking the inverse of both sides, F inverse U and U union V equals F inverse Y, which is just all of X. So we have, and then we can distribute the F inverse because the inverses work nicely. So F inverse U union F inverse V equals X, and these are both open sets which satisfy the properties for X to be disconnected. So in this case, X must be disconnected. And so if X is connected, Y cannot be disconnected, so Y must be connected. So we can show if X and Y are connected spaces and the intersection of X and Y is not empty, then the union of X and Y must also be connected. So we're going to prove this via contradiction. Assume union X and Y is disconnected. So we have some open sets U and V who have null intersection, and they both contain some of X union Y, and their union gives us all of X or Y. So first assume U contains all of X. In this case, U must also contain all of X and Y, so it contains some of Y too. So in that case, U intersection Y, which is non-empty, and V intersection Y, which is non-empty, these are both open sets in the subspace of Y. And these both satisfy the conditions to make Y a disconnected set, which is a contradiction. So now assume X does not contain all of X, but in this case, V must contain the rest that isn't contained in U. And then U and X is an open set, V and X is an open set. They're both disjoint, and their union gives us all of X. And so then X must be disconnected. But this is a contradiction, so these sets don't exist, and X union Y must be connected. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.